All right, well, we're going to be looking at acceleration today, which is the second derivative of position. But before we get into today's lesson, I want to go back and look at a question that a few people had been asking about when we met last week. And so this is one of the questions that you guys had assigned. I thought I would go over it because I'm assuming if a few people had questions, a few more probably did that didn't ask. So we're going to go back just down to how to map out the particle or the position of a particle. So this is the exact question out of the textbook. You were given a formula, and then you were asked first to find the velocity after 1 second and 3 seconds. Well, if we're given a position graph and we're asked to find velocity, that means the first thing we got to do is take the derivative. So velocity with respect to time is the derivative of the position with respect to time, which would give us 2t minus 4. So if we want to find the velocity after 1 second, so that means the velocity at exactly 1 second, this is instantaneous velocity, it's going to be 2 times 1 minus 4, so negative 2 meters per second. If we're finding the velocity at 3 seconds, 2 times 3, 6 minus 4 is positive 2 meters per second. Next question, it asks, when is the particle at rest? So the particle would be at rest when velocity is equal to 0. So when v of t equals 2t minus 4 equals 0. So we're looking at when 2t minus 4 equals 0. So the first thing we're going to do is factor. So 2 times t minus 2 equals 0. T minus 2 equals 0, so t equals 2. So the particle is at rest at time equals 2 seconds. So at this point, we're just plugging and playing based on the information that we're asked for. So it says, when is the particle moving in a positive direction? In other words, when are the values for the velocity going to be positive? So this t equals 2 seconds is a critical point. That's going to be a turning point. And so we know from the starting point here that the position formula is here, and the time is greater than or equal to 0. So we have to first figure out, well, what is, we've got the time here, we're setting up our interval chart here. We've got our time, and our time is going from 0 to 2 seconds, not including the 2 because that's a critical point, but including the 0. And then our velocity after that turning point is going from 2 to infinity because there's no other critical points. So we have to find numbers or time values that are between those intervals to decide whether it's a positive or negative direction. Because we've already done some of this legwork in a previous question, we don't need to rewrite it down here. So we're just looking at is velocity positive or negative. So from time 0 to 2, a number that would fit in there is 1 second. So at that point, our velocity was negative. And from 2 to infinity, a number that would fit in there is 3, and that was a positive velocity. So our velocity is negative from 0 to 2, and it's positive from 2 to infinity. From there, we need to actually draw out our motion of our particle. But before we can do that, we have to figure out the position of the particle at time equals 0. So that goes back to our original formula. So we plug in s of 0. So at time 0, 0 squared minus 4 times 0 plus 4, the position is at 4 meters. So there's 0, 1, 2, 3, 4. So at time 0, it's starting at 4. Now, we know that there's a critical point at 2. We know it has a turning point at time equals 2. So s of 2 is 2 squared minus 4 times 2 plus 4, and that's 0. So at time equals 0, we're at 4 meters. And at time equals 2, we're at 0 meters. And we know that the velocity is negative between 0 and 2. So that means we're going to the left, and then it turns, and now it's positive. So now it's going to the right. So hopefully that gives you a little bit of a visual for that question. We're not going to be mapping particles in this next piece. We're just going to be looking at the derivative components. So on to acceleration. Acceleration is the rate of change of velocity with respect to time. If you look back at your other notes, I believe I missed putting the word position in there. So velocity is the rate of change of the position with respect to time, and acceleration is the rate of change of velocity with respect to time. So if we look first, just a reminder or refresher about average acceleration, this would be our secant line. So our average acceleration would be velocity of time 2 minus the velocity at time 1, all over time 2 minus time 1. When we're doing instantaneous, this is our tangent line, and this is where we're doing the derivative. So the instantaneous acceleration would be the derivative of velocity. So acceleration is the derivative of velocity. Velocity is the derivative of position, and that means that acceleration is the second derivative of position. So we just have a couple examples today to go through. Example number 1, the position function of a particle is given. S is in meters and T is in seconds. And if we want to figure out the velocity at any time, then we're taking the derivative of the position. So this is just like S that we used before. So velocity at any time is the derivative of the position. In this case, that's F prime of T, and that is 3T squared plus 4T plus 2. If we want to find acceleration at any time, acceleration with respect to time is the derivative of velocity with respect to time, which is the same as the second derivative of position. And that would be 6T plus 4. Now, if we're asked for average acceleration, remember average acceleration means we're taking the velocity at time 2 minus the velocity at time 1. So we'd actually be using our velocity formula here. So average acceleration versus instantaneous. So V of 5 would be 3 times 5 squared plus 4 times 5 plus 2, which is 97 meters per second. And the velocity at time 0, 3 times 0 squared plus 4 times 0 plus 2 is 2 meters per second. So if we were figuring out our average acceleration, it would be 97 minus 2 all over 5 seconds minus 0, which would come out to 19 meters per second squared. So a little note on units here. I had meters per second divided by second. So you'll hear some physics teachers say meters per second. Well, if we use our multiplication rules, meters over seconds times 1 over seconds equals meters per second squared. All right, again, if you've done physics, you're probably familiar with that. You've probably heard of acceleration due to gravity, but that's why our units are meters per second squared. If we want to know the acceleration after 3 seconds, that means we're looking for instantaneous. We're looking for exactly 3 seconds. Here we're using our derivative. So acceleration at time 3, we go back to our derivative was 6t plus 4. So 6 times 3 plus 4 is 22 meters per second squared. All right, so we just got one other example to look at today before you get onto your assignment, and that's looking at a ball being thrown upward. So a ball is being thrown upward with an initial velocity of 24.5 meters per second, and its distance above the ground after time in seconds is given by that formula there. Again, F of t is the same as our position. It can be the same as S. So we're being asked to find the acceleration of the ball. So in order to find the acceleration, we need to do the second derivative of the position. So we start off by finding velocity. So velocity is the derivative of position, which is 24.5 minus 9.8t. And then acceleration is the derivative of velocity, or the second derivative of position, which is negative 9.8. Now that number should be familiar. That's our acceleration due to gravity. This would be negative 9.8 meters per second squared. So that's acceleration due to gravity. Now the question might come up about the negative, okay? So we have a negative here. And again, if you're in physics, you guys have talked about this already. But the negative there means that the ball is slowing down as it rises and it's speeding up as it falls. Now we'll look at a graph here. I'm going to sketch a graph here. In general, when we look at acceleration and velocity, if we have a negative acceleration, that means your velocity is decreasing. And if we have a positive acceleration, that means your velocity is increasing. So if I were to do a quick sketch here, velocity time graph. So velocity there and time there. And remember that I'm trying to do instantaneous acceleration. That's going to be a tangent line. Well, if I draw a tangent line right there at that point, my acceleration is negative, but my velocity is also going down. So my velocity is decreasing. And if I were to do a tangent right here, my acceleration would be positive and my velocity is actually increasing. So that's just a general rule that we can use. So for your assignment, when you get to class, we're going to be doing page 128, numbers 1 and 3 through 8. All right, guys, have a good night.